talk about what we call stoichiometry. And stoichiometry is basically the study of quantitative, quantity, number, the relationship between, okay, reactants and products, etc., etc. Okay. A chemical reaction involves a specific ratio between the reactant molecules and the product molecules. We know that. That's the balanced chemical equation. The law of conservation of mass, all that stuff. Okay. For example, if we looked at the combustion of methane, methane is CH4. For every 1 mole of this, for every 1 mole of methane I want to burn, okay, we could talk about molecules too if you want, but a molecule is incredibly tiny, right? We wouldn't see that. So it doesn't really make sense to talk about that. We usually talk about 6.02 times 10 to the 23 or a mole of stuff, right? So if I in this case burned, because it is a combustion reaction, if I burned 1 mole of methane, if I took 1 mole of methane, I'd need 2 moles of oxygen to react with it, okay, balanced chemical equation, and I'd get 1 mole of carbon dioxide, and as a result, I'd get 2 moles of water gas, okay, and that's the balanced chemical equation, okay. So for every mole of methane that reacts, I use 2 moles of oxygen are also reacting with it, and I would get 1 mole of carbon dioxide produced and 2 moles of water produced, okay. That's the balanced chemical equation. So what we're going to do here is predict. Well, okay, you know, quite often, like for example in our lab, I said if we wanted to decompose 1 mole of malachite, we'd have to use 222 grams of malachite, the green stuff. That's a lot. Okay, that'd be the entire bottle. Obviously, it would take a long time for it to decompose. We'd only be able to do 1 experiment, and it would basically be you watching me do that. So we don't want to do that. How many times do we actually burn or decompose 1 mole of malachite? Probably never. We don't. We use little tinier versions, right? For example, right? On our last sheet there, we decomposed 0.00. The first number was what? 0.0025 or something like that, or whatever, 24 moles, right? Very small amount. But as a result, we should be able to predict how much product we get from that. So that's what we're going to do here. Look, this is called propane here. If I took 1 mole of propane, it needs to react with 5 moles of oxygen, and that would give me 3 moles of carbon dioxide and 4 moles of water gas. That is the balanced chemical equation for the combustion of propane. Okay? So you would write out the equation, balance it. That would be basically your equation there. Okay? If I use 1.28 moles of propane, how many moles of carbon dioxide should I get from that? Okay? And of course, to figure that out, Stephen, 3.884 moles. And to figure that out, of course, look, it's a 1 to 3 ratio. So times it by 3. Okay, you guys can even put the arrows in there for you. And put down the multiplying part too for me, please. Okay, so I know. Let's get into the habit of that, because that's what I want to see on your quizzes and stuff like that too. So, okay. Look, if I had, let's say, that, you know, you might say, well, this doesn't make sense. It does actually. If I only have 0.3 moles of oxygen available, so if I'm burning propane in a closed container, for example, and I only give you 0.38 moles of oxygen, how many moles, or how much water gas could I probably make from that? Well, once again, you're looking at the ratio here, guys. This is a 5 to 4 ratio. How am I going to get that over from 5 to 4? And the answer is, well, if I got 0.38 moles of oxygen, how much water gas should I get? And the easiest thing to do here, and quite often we'll do this anyway, is, hey, this is for 5 moles right here, this right here. So if I divide it by 5, that gets me down to 1 mole. And then now I still need to move it over to 4 moles, so I multiply it by 4. So divide by 5 times by 4 if you want to come up with a different system. If you want to divide by 1.25, whatever, okay, works the same. Just make sure you don't round any numbers. And here you should get, of course, 0.30 moles. Okay, good so far? Yeah? So you're using the balanced chemical equation to move N around. Okay? This one here, I got 3.15 times 10 to the negative 2. How many moles of oxygen would I have to use to make that for the carbon dioxide there? Well, once again, can I go backwards like this? Sure you can, okay? This is the ratio that I need to use. So it is a 3 to 5 ratio now. So I'm going to divide by 3 and times it by 5, okay? You don't have to put it back into scientific notation for right now. It's fine. When you do that, divide by 3, times it by 5, I think you get 0.0525. Is that right? So I'll just write that down, 0.0525 moles. Okay? Once again, we should use significant digits, and we'll talk about that when we get to the actual problems today. And one last one here. If I get 758.3 moles of water produced, how much propane would I have to burn, basically, to get that amount? And the answer is, well, let's see. It's a, once again, 4 to 1 ratio. So I can simply go from 4 to 1, divide by 4, right? And if you really want to, you could put times 1 if you want, but divide by 4. Yeah. So doing that, you're going to get, I should know this here, divided by 4, 189.6. And once again, I used rounded numbers, 4 significant digits, so I kept with 4 there. Okay? Is that good? Yes? There is a relationship, like I said, it's stoichiometry, okay? And there's a relationship that exists between, of course, for every mole of propane that you burn, there is 5 moles of oxygen, 3 moles of carbon dioxide is produced, and 4 moles of water, okay? And you have to remember, we're not adding these together. So you might say, well, yeah, but 1 and 5 doesn't give me, that's 6. This is 7. How is that possible? You're not adding them up. You're combining them, rearranging them. So yeah, they might not add up to the same thing that you started with, okay? But it's all still there, trust me, because that's the balanced part of the chemical equation, right? Has to be. So, like I said, it's not a matter of adding this and this together to get the same thing on the other side. It's a matter of adding stuff together, rearranging it, and coming out with some new products. They're going to be different, obviously. That's the purpose of chemical reaction. So, how are we going to use this? Well, today we're going to look at something called mass stoichiometry. Mass stoichiometry involves masses, believe it or not. And same thing, obviously. You're going to use that balanced chemical equation to figure out the mass that should be produced or should be required to make something else. Okay? So, to do that, here's our first example. In order to do these questions, obviously, I don't have to tell you this, but it says what mass of zinc must react during a formation reaction to produce 50 grams of zinc oxide. You need to be able to come up with a chemical equation for this. If you cannot, or if you get the wrong one, you're going to get this question wrong. And pretty much every other question wrong in this unit. Okay? So, you need to know this is a formation reaction. We want to make zinc oxide. So, formation, zinc oxide. 2 plus, 2 minus, solid because it's not a compound, of course, right? What are the things I need to make zinc oxide? Well, probably a little bit of zinc and a little bit of oxygen. Oxygen comes in 2s, of course, okay? That is a simple formation question that you need to be able to do, and I guess we'll find out if you did something like that on your quiz today or not, okay? You need to balance it. Step 1, you're going to write this equation out. Proper equation, in this case, formation. Step 2, you want to balance it. So we're going to have to put a 2 there and a 2 there to balance it. Okay? Those are always your first 2 steps. Always. Chemical equation, balance it. Step 3, put the information in the right spot, just like in Unit 3, if you remember. 50 grams of zinc oxide. I want to make 50 grams of zinc oxide. They're asking me what mass of zinc must react to produce 50 grams of zinc oxide. That's what I'm looking for. Okay? That's step 3. Put all your information down. Yes? Good so far? Any questions? Okay? Then you're going to start filling stuff in, of course, to help you do this. Well, what could help me do this? Let's see. Once again, I know that basically 2 moles here makes 2 moles here, right? It's actually turns out to be a 1-to-1 kind of ratio, right? For every 2 moles that I use of zinc, I get 2 moles of zinc oxide. So that's kind of handy. Well, I'm going to find the molar mass. That would probably be a good thing. Zinc oxide, I think it's 81.41 grams per mole. And you're going to find N. Okay? Now, we will talk about molar masses in a second here. I'm going to finish this problem. I'll go back to that for a second here. So just let me finish here. So 50, I got the mass, I got the molar mass. I can find N from that. Okay? Once again, so that's about 0.6 something. 50 divided by 81.41 is about 0.614 moles. And once again, obviously, don't round that number. Well, let's see. 2 moles gives me 2 moles there. So if I made 0.614 moles, I guess over here I probably made I used 0.614 moles there, right? Correct? If 2 moles gives me 2 moles, then I have to use, if I wanted to make 0.614 moles, then I'd have to use 0.614 moles. If you're not happy about that and you say, how am I going to get from there to there? Well, you could divide this by 2 if you really wanted to, and then times it by 2 to get over to here, which is 1. Yes? Okay. True? Yeah. Molar mass of zinc, I know that, 65.41. Multiplying those two, I can figure out how much zinc I had to use in this equation. So I'm going to take that, times it by 65.41. Remember, don't round at any point until the very end, which I'm going to do right now. It's 40.2 grams, 3 significant digits because there's 3 in the question. Okay? 3 significant digits because there's 3 in the question. All right? Good so far? That's it. Yes? Now, a couple things. Because this is where we can go wrong, so you just need to listen very carefully. All these questions are going to be the same. Okay? You can do this. Well, they get a little bit more complicated sometimes, but that's pretty much it. This is pretty much what we're going to do for the rest of this unit. Okay? In one shape or another. Yes, we'll change a few things up, but if you can do this, you can do this. Okay? This is not hard. But listen, there's a couple things you have to remember. This number out front is not, I repeat, not used for the molar mass. Okay? Has nothing to do with molar mass. Okay? This number out front is not used for the molar mass. The molar mass comes from this right there. Likewise here, molar mass comes from that right there. Okay? Do not use the molar mass with that number out front. The number out front, what's its job? Its job is to get you from one place to another place, okay? To make it simple, without technical mumbo jumbo. It's how I get from here to here. It's how I get from here to here, etc., etc. That's the number out front. That's its job, okay? In this case, it was a 2 to 2. So that's the job. It goes from 2 to 2, and you might say, well, we didn't really do anything with it. No, because it's a 2 to 2. It's a 1-to-1 ratio, so we didn't have to do anything with it. Okay? But that's the number out front. That's its job. Okay? So don't include the number out front for the molar mass. If you do, it may or may not work out for you. And the chance that it probably doesn't work out for you is probably very, very good. Okay? So don't include the number out front for the molar mass. Just look at the compound. Figure that out. Use the numbers out front to get from here to there, to there, to there, whatever. Okay? Next example. There you go. I'm going to let you guys write out the equation for this. This is a gooder. Okay? This is how it gets trickier. I give you questions like this, which is a little more complex. Once again, there's no point in worrying about 75 grams if you can't write out the equation for this. Okay? So that's where it's going to get trickier. Okay, you guys can keep working here. Don't look up here. That's fine. I just got to get going here because we got to finish this before the end of class here. So don't worry about me. If you're done, that's fine. Bismuth 5-thiosulfate looks like that. It is an ionic compound. It is a solid. When you heat it up, you're going to get bismuth, sulfur, and oxygen. Molecular elements, each element by itself, of course, hopefully. That's what you did on your quiz today when you do decomposition. Balancing-wise, I'm going to tell you right now, bismuth is not hard to balance. Oxygen won't be too bad. The problem is going to be, once again, as we talked about this, phosphorus and sulfur are usually problems. In this case, sulfur. We got 8 sulfurs on the right side. We got 10 on the left side, yes? Because there's a 5 out here and 2 sulfurs. So 10 sulfurs on that side. The lowest common multiple of 10 and 8 is what? 40. Now, does it work with 80? And the answer is yes. Okay? But I will take off a mark because what's going to happen is you are going to get twice everything. You can just go back and reduce it after, but it does work. And you'll find that every number that you use to balance is a multiple of 2. So you just go back and divide everything by 2. Okay, that's all. So make sure that that's the case. It is 40, so we're going to put a 4 out here. So 4 times 10 sulfurs is 40, and 5 times 8 sulfurs there is 40. Okay. I got 8 bismuths this is, so I'm going to put that there. And I got 15 oxygens times the 4 out front, so that's 60. Half of 60 is 30. Okay, so that's a good balancing one. I like that. Yes. We have 75 grams of this bismuth 5-thiosulfate. We want to figure out what mass of sulfur can be produced. Now, if you didn't write out this equation, if you thought you were going to do bismuth ions and thiosulfate ions, it's not going to work. Because thiosulfate ions, what's the molar mass of sulfur is not even isolated in that, S2O3 2-, right? So that's why I kind of harped on you guys at the beginning. I said when you do single decomposition or formation, each element by itself, okay? That's what you need to have. This you can figure out, okay? Molar mass of bismuth 5-thiosulfate is, I believe, 978.66 is what you should get. And when you divide those two, I believe you get about 0.076. Yeah, 0.0766. And I need to move that over to there. Okay, well, and to move that over to there, let's see. Now I will use the numbers out front. So 4 to 5. Divide by 4, times it by 5. All right? Divide by 4, times by 5. Over here I get about 0.0957. Molar mass, 256.56. I multiply those two, of course, and my final answer, all said and done, significant digits as well, 24.6 grams. Okay? We could go to the lab and you could test this out. You could. We just did it the other day with malachite. If you don't believe me, I could go find some bismuth 5-thiosulfate for you. You could do this exact same thing. Okay? And if we could isolate the sulfur, which we'd have to do, it's a little more tricky with this one because we also get bismuth eventually. And to break that ionic compound apart would be pretty tough to get those individual elements. That's why we did the one we did yesterday, because it gives you copper 2 oxide, another ionic compound. So it's a little bit easier. Okay? But if you were able to heat this up hot enough, that's what you would expect to get for sulfur, 24.6 grams. Okay? Good? All the questions are like that. Okay? We're going to add on to it, so don't think that you can go to Mexico now and just be like, hey, I'm done, right? We're going to add on to that, so it will get a little bit more tricky, but this is the general thing that we're going to be working on for the rest of this unit, okay? We're going to do solution stoichiometry, C equals N over V. We're going to do gas stoichiometry, PV equals nRT. We're going to do limiting reactants, so which one runs out first. That's a little more complicated. And then after that, we're going to do some titrations, and we're pretty much done, okay? But it's going to take a little while, okay? All right, for homework, you guys have a sheet on the back there. You'll have these done for tomorrow. But listen, and I know it looks like a lot. You're going to be like freaking out. Oh my God, there's so many questions. But listen, number one, you're going to write out the equation, okay? That's the first thing, you're going to balance it. And then A is based on that equation. B is based on that equation. C is based on that equation. So the equation is only really written once, okay? And then A, B, and C just follow along with that equation. Obviously, though, if you can't get answer A, the chance of you getting B and C is probably not good either, because A, B, and C all depend on that first equation. So there could be something wrong with it. It could be a molar mass thing. I don't know. Show me your work so I know. But your first one here is what? Balanced equation for the formation of iron 2 thiocyanate, right? So each element by itself, figure that out, okay? And then you're going to basically line up stuff. I want to see stuff lined up because, number one, it's easier for me to mark, but also when we add stuff on, it's going to be easier, okay? So like, for example, when we get to this here, not so much that one, but this one here eventually, we're also eventually going to put some stuff in this section here, okay? And then we're going to have to predict the product based on which one runs out first, kind of thing, okay? So it's really important to keep stuff straight, nice and neat, underneath each reactant, product, whatever. Make sure it lines up, okay? Please. It makes my life easier, makes yours easier, and I can quickly see where things went wrong, and I can quickly mark them too when it comes time, okay? So I'll let you guys work on those for a few minutes here, and if you guys got a little extra time, we still need to go over molecular ionic, net ionic. I know we do. That's lesson 4. So we still need to do that. We'll do that tomorrow as well, and we'll go over these, and we're going to build on this as well tomorrow, okay? I'd say tomorrow is probably pretty important because I think tomorrow, if I'm not mistaken, is limiting reactants, which is probably the toughest one tomorrow. If you can say it's tough, I don't know, but it is probably your next toughest one, and then after that, it's all the same stuff, okay? But all right, so try not to miss tomorrow if at all possible, and we'll talk. Yeah, well, that's it, I guess. Okay, questions?